Good morning or good afternoon, everyone. Once again, this is Mr. Steele. I'm going to be working through the second lecture in this series, working through this analysis unit with you. In this lecture, that isn't going to be a direct follow-up to what we did yesterday, but more kind of completing some extra ingredients and pieces so that we can move forward with the rest of calculus. We're going to be talking about a concept or a tool or just a simple theorem called the Mean Value Theorem. It's going to complete our trifecta of value theorems. So my goal in this lesson is to first start by reminding you of what those other two value theorems do, using visuals to kind of help add to the statements of the theorems themselves. Then we'll inspect the mean value theorem itself. I'll kind of translate it for you so you can think about it in a more practical term. Then we'll look at some visuals for it to help you see what it is that the mean value theorem is finding, and of course when you can't actually use the mean value theorem, like when it doesn't apply. After that, we'll solve some problems, show you kind of the traditional context in which you'll be asked to apply the mean value theorem. We'll talk about some of the more exotic contexts where you might need to apply the mean value theorem. And if there's time, we'll wrap up by talking about a corollary of the mean value theorem, a sort of follow-up called Rolle's theorem, that also gives us very similar information, but that can be interpreted in a specific context to help us with that idea of optimization. Before we start, though, as I said, I wanted to begin by just going through what those other two value theorems were that we hit, just to kind of remind you of the sort of things that we've been able to guarantee. And if you'll recall, with both the intermediate and extreme value theorem, what we've been given is an expectation of continuity. If a function is continuous, then we can say a whole lot about what happens with that function in between those two endpoints. Starting things off, when we dealt with the intermediate value theorem in the very beginning, and again, you don't need to write this stuff down, it's in your notes already, I'm just using it to remind you and provide context. So with the intermediate value theorem, it says that if f is continuous on a closed interval from a to b, and f of a is less than some k value is less than f of b, so setting those things up, we will in the picture in just a second, then f of c is equal to k for some c in AB. So visualizing this a little bit for us, here is, according to our picture, the value f of a. Up here, okay, it's going to miss my axis, but oh well, is the value f of b. And what the intermediate value theorem says is if f is continuous, you can choose any value k somewhere in between f of a and f of b. Notice right here that definitely satisfies the inequality shown right here. And if k is between those two values, then f of c has to equal k for some c inside that open interval. So what that means is actually, we'll draw that. If I draw over to the curve, you can see that we can drop down and we can find some corresponding c value. And notice that c is between a and b. So basically what this is giving us is the intermediate value theorem is giving us kind of a betweenness existence, or the existence of some value that's between two other ones, assuming we have continuity. We're guaranteed to find a spot on the curve and show that the x value that corresponds to that spot on the curve is going to be inside the interval that we were looking at. So that is the intermediate value theorem. We used it early on to find zeros. We've used it for other purposes as well. Yesterday, we took that a little bit further, and we talked about the extreme value theorem, which says if f of x is a continuous function on a closed interval a to b, which again our picture illustrates really nicely, then f has both a maximum and a minimum value on the closed interval a to b. So in this case, like we didn't really talk about in context of x values, but in a sense what this says is that there is a smallest value on that curve, and there is a largest value. Oh, that was a terrible horizontal line, but setting that aside for a second. So there is a highest and there is a lowest value. So there is our min value, there is our max value. And in fact, you could even say something like f of c1 would have to equal the minimum value, and f of c2 would have to equal the maximum value, and both c1 and c2 would be inside the interval from a to b. And in this case, we guarantee it over a closed interval because it's always possible that our high or low points could be at one of the endpoints. So that is the extreme value theorem. The intermediate value theorem guarantees that we have some value in the intermediate area, or the middle of the region. The extreme value theorem guarantees that we have extreme values on the interval that we're looking at. So the question you might ask yourself is, what would the mean value theorem guarantee? And if you think about the word mean, although it might make you seem angry, like I'm mean, I'm making you learn while I'm gone. Yes, that is a possibility, of course. But If you think about the word mean in a mathematical sense, mean is another word for average. And in fact, the mean value theorem guarantees that there's a place where there's a particular average value, or in this case, an average rate of change on the curve. So moving forward, here is the mean value theorem in all its glory. And I've modified this lesson from previous years to try to get a better flow. It's always my goal anyway. So this is the mean value theorem. The mean value theorem states that if f is continuous on the closed interval AB and differentiable on the open interval AB, then f of b minus f of a over b minus a is going to be equal to f prime of c for some c value in between a and b. So in this case, we've added this whole new component into our value theorem. No longer are we just requiring continuity, although we still do. We're requiring differentiability, and then we're getting the existence of some c value where f of b minus f of a over b minus a is equal to f prime of c. Now, for the sake of argument here, I want to really quickly translate and bring over that last expression. F of b minus f of a over b minus a is equal to f prime of c. So what this is saying is that the average rate of change, which we know is just the slope between 2 points on the curve, the average rate of change has to be equal to the derivative, which we also know as the instantaneous rate of change. Yeah, these are long phrases to write, I apologize. So in other words, this guarantees, given some conditions, of course, are met, that there's going to be a place where the average rate of change is going to be equivalent to the instantaneous rate of change. Now, taking that for just a second, we can draw a picture and kind of illustrate what it is that I mean, but let's translate that really fast. The average rate of change is a slope. Of course, it's y2 minus y1 over x2 minus x1. But it's not just the slope of any line, it's the slope of the secant line. So in other words, if we draw a secant line through the endpoints, we get, of course, what we would call the secant line. And the slope of that secant line is the average rate of change. So I'm going to attempt to do this here. I don't have a ruler handy, do I? No, I don't. Dang. So I'm going to try to make this as good as possible. If you're wondering why I'm not doing some other technique, it's because, or I'm not using some sort of line tool. They don't exist in Windows Journal. I apologize. But there is our secant line. So we've just calculated the secant line, and of course that secant line has slope f of b minus f of a over b minus a. And there should be no surprises there. Kind of weird, but that's what we've got. So from here, though, the second thing that we have is this mention of the derivative, or the instantaneous rate of change. So in other words, what we're talking about there is the slope of the tangent line. So in our case, we've said that those two slopes, the slope of the secant line, or the average rate of change, and the slope of the tangent line, or the derivative, have to be equal at some value in between the endpoints. So the slope of the secant line matches slope of the tangent line in the interval. That's what it is we're looking at. And again, given certain conditions are met on the function. So if two slopes match, you might recall from what you guys probably would have called Math 1 or Math 2, that means that the two lines are parallel. So in other words, these two lines are going to be parallel in order to satisfy the mean value theorem. So looking at up at our picture, if I steal that thing really fast, get rid of the dumb little line that I drew, and we imagine taking that expression and trying to match it to the curve somewhere in the middle, you'll notice that we can find a couple secant lines that actually satisfy what we would call now the mean value theorem. Right there, for instance, there's one such secant line. So let's read that. There we go. So right there, it looks like we have a spot where the slope of the tangent line matches the slope of the secant line. They're parallel. But that's not actually the only value. In fact, there's one that looks like it's really, really close up here. Actually, might be a pretty good one right there. Looks like there's a spot right there. So we have what looks to be a second value. And we even have what looks like a third value. And again, you can see my line drawing skills aren't perfect, but it looks to me like we have a third spot right there. So what this would tell me is, from looking at the picture, each of those three dots tells me that there are three values that satisfy the MVT. So we're looking for places where the slope of the secant line matches the slope of the tangent line. And in a sense, what that means is we're trying to find the places where the secant line slope, where the secant line slope is equivalent to the tangent lines. Or, better yet, places where the tangent line is parallel to the secant line. And again, if you're looking at this going like, okay, fine, whatever, like I'll give you a little bit more, but keep in mind this isn't the most practical skill in the world. It's not something that's just going to immediately like be the easiest thing and answer a bunch of huge questions. Really, the reason we attack this is because it lies underneath a bunch of the major proofs of the course. So keep in mind that this isn't the most exciting tool that we're going to ever hit, but it is an essential tool. And that doesn't mean, value theorem, that you shouldn't pay attention to what's here. So you're going to be tested on this as well, so if you're looking for something really practical, there's your motivation. So we're talking about all this different stuff, we're looking at the mean value theorem, we're trying to draw and figure out where, or we're trying to guarantee the existence of, that's a better way to put it, we're trying to guarantee the existence of some spots in the interval where the tangent line will be parallel to the secant line. I should have said that at the very beginning, I'm sorry. That's what we're looking to do with the MVT. Now, to kind of help us move forward here, what I want to do is I just want to visualize a little bit. And I've kind of broken down a tool that Mrs. Formaker created a few years ago to just kind of offer a few quick examples. Because in the interest of time and the interest of not being able to kind of answer your questions myself, I want to make sure that we went through some of these pieces with as quick, expedient a movement as possible. So in here, the first thing I want to do is I want to help work on visualizing the mean value theorem. I know I did on that previous example, but it might have been a little bit harder to actually see. So in here, what we've got are a parabola. In fact, we could probably figure out what the equation of this parabola is, but I'm not going to worry about that right now, even though I do think it is 4x minus x squared or 2x minus x squared, something like that. So anyway, we are given this parabola called h of x, and we're told that we're looking on the interval from 0 to 3. So what I'm going to do is I'm first going to put some marks on the graph of this parabola at 0 and 3. So through those endpoints, 0 and 3, of course we can draw a secant line. And it looks to me like that secant line has slope 1, by the way. Not that it matters, but it's what it looks like to me. So there is our secant line. What the mean value theorem says is that if on our interval our function is both continuous on the closed interval and differentiable on the open interval, then we can find at least one spot where the slope of the tangent line will be matching the slope of the secant line. So following that same strategy from before, let's see if we can actually estimate about where that occurs. Boom. So there looks like we've got a spot. If I had to guess the location where it seems to hit, it looks like it hits about right there. And then from down here at the bottom, what this asked us to do is to estimate the x value where it occurs. I deleted the instructions, unfortunately, that was my mistake. If we're looking, we're just trying to say, well, what is that x value that we're guaranteeing here? And if you're asking me, I'd say that that x value, or the c value if you want to call it that, would be approximately 1.5. So it looks like 1.5 should be the value that satisfies the mean value theorem because it produces a tangent line that is parallel to the original secant line. So we chose 0 to 3 for that first one. The second one asks us to choose 2 to 5. So let's see if we can do that. There's 2, so it might be kind of tough to draw. 5 is all the way down there, so it can be a little bit of a challenge. So there is what appears to be our secant line. Again, the mean value theorem says that there's going to be a spot where the tangent line is parallel to it. And again, I've been sliding through that continuity and differentiability spot just because we're going to deal with that in just a moment. But once again, the question always comes up, well, can we find such a spot? And it looks to me like we found it. Again, knowing that I'm not doing a perfect job of drawing this, looks to me like we have a parallel tangent line right there. And following the same pattern as before, if we kind of write down and try to see what that x value is, looks to me like that x value is at approximately 3.5. So again, what we're saying here, by the way, if we're looking at this in equation terms, what we're saying on the first one is that h of 3 minus h of 0 over 3 minus 0 is equal to h prime of 1.5. In other words, we're finding the c value that's guaranteed by the mean value theorem. It guarantees there should be one there. We just used a picture to estimate one. Over on the second one, we have h of 5 minus h of 2 over 5 minus 2, which is going to be equal to h prime of about 3.5. So that's kind of what we're drawing in our pictures. We're visually solving this equation and approximating the solutions to it. So that's all well and good. That helps us really nicely to look at the mean value theorem in that way. But keep in mind, the mean value theorem doesn't say that this is true for every single function in the world that we're ever going to run into. In fact, there are restrictions. So the question to ask yourself really briefly is, well, is this always possible? And more importantly, since you realize it's not going to always be possible, otherwise it'd be a dumb question to ask, it's worth pointing out that we should think about when it doesn't work. So to help us with this, I've brought the mean value theorem over just so we can kind of see what the issues are. So the first issue that pops up is what's telegraphed in the statement of the mean value theorem. It says if f is continuous on a to b. So what if f is not continuous? So why is it that that might stop us from guaranteeing us there's a place where the tangent line is parallel to the secant line? Well, in this particular example, we're using 0 to 2. So I'm going to mark them on our picture. Hopefully that green is visible enough for you. So right there is the tangent line that we're guaranteeing the existence of. And notice on that interval from 0 to 2, there's a discontinuity. In fact, I could ask you what type of discontinuity is, and you would say, do, 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 do. If you knew 80s music, that joke would have made sense. But yes, there's a jump there. Basically, there's a jump. The left-hand limit equals 1, and the right-hand limit equals 4. So those two things aren't equal, so there creates a jump, or a break, or a gap in our function. So with that in mind, with that discontinuity there, you can see why it is that this doesn't guarantee there's such a tangent line. Just look at our graph. Like if I try to place this somewhere, I'm always crossing the graph. I'm definitely not matching the slope. And while there probably is a spot over to the right of our interval, what we're missing is a value inside that interval itself. In fact, look, the slope of that secant line is going to be greater than 0, but notice that these slopes would be negative no matter where we drew them on 0 to 2. That's because continuity removes the requirement that our graph go smoothly through every possible value. So unfortunately, we're missing something here, and that means that we have 0 such tangent lines, which is of course why the mean value theorem excludes non-continuous functions. So we've seen our first possibilities. If f is not continuous on that interval, then unfortunately the mean value theorem does not apply. So it's just kind of out. The second possibility here is that f is not differentiable. So if f is not differentiable, that means that there might be places where the derivative abruptly changes values. And in fact, look at that. Differentiability is required on the open interval. Doesn't matter what happens on the endpoints, but it is required on the interval. So looking at our picture once again, if I draw in my endpoints and then draw the secant line, we can try to locate a place on this non-differentiable function where the slope matches. But unfortunately, if we look, our slope is positive, then suddenly our slope is negative. So if we want to find the place where it matches up top, unfortunately, what we have there is nothing. There isn't such a place, and the reason is that is a sharp turn. And a sharp turn, of course, means that our function is non-differentiable. So the mean value theorem does in fact guarantee that there is a tangent line, which would seem to disqualify these two non-tangent line existing situations, except those two properties required by the mean value theorem are essential. Otherwise, we need not apply. If f is continuous, as in there's no holes, there's no vertical asymptotes, there's no jumps, and f is differentiable, meaning no sharp turns, no vertical tangent lines, and no discontinuities, which you already talked about, then we're allowed to say that there's a tangent line whose slope matches the secant line. Only under those requirements. And again, this page illustrates some situations that show you if either of those two properties fails, it does not work necessarily. Now, we'll warn you there are some situations where it could be discontinuous or it could be non-differentiable and you could still find the value. But of course, the fact that any exists that way means this statement does not hold for either of those two things. Okay, so I know that's a lot. It's been a ton to process so far. That's why we're going to move forward and jump right into a problem. That's what I want to do. Let's actually attack this concept. So in here, what we're going to do first is just do a standard mean value theorem problem. We're going to find the value or values guaranteed by the mean value theorem for the function x cubed minus 1 on the interval from 1 to 4. So that's where we're going to start. And to assist you with this, I'm going to go ahead and create a plan on the side. So we're going to have a plan of attack, like some steps to follow to work your way through this. I know it might be a lot so far. It's not actually a lot to actually do. So our steps here. Let's begin with step 1. The first step that we're going to hit is to verify that we can even use the mean value theorem in our situation. So to begin with, step 1, verify the mean value theorem applies. So we want to make sure that all properties or all necessary conditions are met to allow us to apply the mean value theorem. Now, we mentioned it earlier. There are two things that are required for the mean value theorem to apply, very similar to other ones that require certain things. In this case, the first thing that we're required is specifically continuity, and it's going to be continuity on the closed interval a to b. So in our case, we're going to need to look and make sure that the function x cubed minus 1 is continuous on the closed interval from 1 to 4. The second property we need to check for is differentiability. We need to make sure that the derivative exists at all those places and there's no sharp turns or vertical tangents or what you will on the open interval a to b. So it doesn't matter if there's a sharp turn at one of the endpoints, just that there's not in the middle of the region. Because if there is, we could have a situation like the previous page, right here, where we just don't get that value in the middle. So let's check first that the mean value theorem applies to our function. Well, in this particular case, I've made it pretty easy for you. So on the interval from 1 to 4, but on every interval for all real numbers, x cubed minus 1 is a polynomial. And the nice thing about polynomials, we've mentioned many, many times before, is they are infinitely differentiable as well as, of course, continuous. So what that tells us is that f is continuous and differentiable. And we could say on 1 to 4, but really this is a, by definition, continuous and differentiable function. So in other words, at all x values on its domain, which is all real x values, this function is continuous and differentiable. And of course, our reasoning here, what's important about saying that? That means that the mean value theorem applies. So that's telling us that we can guarantee that there's going to be some place where the secant line through our endpoints is going to be parallel to some tangent line in the middle. Or we can guarantee that there is a tangent line in the middle that's going to be parallel to our secant line through the endpoints. So our first step was to verify the mean value theorem applied. And if that's true, our second step is where we start to do the actual computation, stuff that people are usually most comfortable with. So second, we need to compute both components that are required for the mean value theorem. First, we need to compute the average rate of change. So we need to compute what we would think of as the secant line slope. And we're going to use it over the course of our closed interval. And then second, we need to compute the derivative. That way we'll be able to compare those two and try to figure out what the equation is that lets us solve for the x value we're interested in, that c value in the middle. So in our case, the first thing is going to be to compute the average rate of change. And we're on the interval from 1 to 4. So that means we're going to be computing f of 4 minus f of 1 all over 4 minus 1. So looking up at our equation, that's not going to be particularly hard. That's 4 cubed minus 1, although I will point out that I'm using these parentheses. It's a habit of effective mathematicians, because of course that means we're not going to misattribute or misdistribute that negative sign. So f of 4 is 4 cubed minus 1, f of 1 is 1 cubed minus 1, all divided by what amounts to 3. So from here, that's 64 minus 1, or 63, minus 0, all over 3 equals 21. So again, what we've just found is the average rate of change. This is the secant line slope. And I'm going to write that in there as well. Just trying to provide as much context on this first one as possible. So there is our average rate of change. That's half the equation we're trying to solve. The second thing we have to figure out is what is f prime of x. So we need to compute the derivative of that function. Well, that function's pretty easy to differentiate. It's 3x squared. So that is the formula that we use to calculate out what the slope is on this curve at any x value. So what we've just found is the average rate of change and the derivative themselves. So our next move is, of course, to bring them together. So we'll call this third step. I really want a darker green. Let's get darker green. Heck yeah. There we go. Our third step is going to be to solve the equation. And included in solving it, of course, is setting up the equation, which we have not done so far. So we're going to solve the equation. We want to solve f of b minus f of a over b minus a is equal to f prime of c. So in here, we found f prime of x. We know what the average rate of change is. So that means that we're going to be solving the equation, doing it in the correct order we have on the right. 21 is equal to 3x squared. So pretty easy equation to solve. We can divide both sides by 3. We'll get that 7 is equal to x squared. And then some square rooting work on both sides is going to get us two possible answers. X equals negative root 7 and x equals root 7. So there are two answers. These are two places where the slope of the tangent line is going to match the slope of the secant line. And so in many people's cases, they immediately go, yay, look, I'm done. But there's actually something very important to do before you finish the problem. In fact, this answer, while you might be willing to pat yourself on the back and feel really good about, is actually incorrect. And the reason is, we need to confirm that we get an answer that's inside the open interval. So we need to make sure that C is a member of our open interval A to B. So in other words, what that means is we need to check back to the region that we are calculating the secant line slope on and ensure that we only present the values that are inside that interval. There may be other spots where the tangent line is parallel to the secant line, but if they're outside their interval, they're not guaranteed by the mean value theorem, so they're just kind of irrelevant to us. It just doesn't matter. It's not something we need to investigate. So in our case, we were on the interval 1 to 4, so we're curious about whether or not those values are in the interval from 1 to 4. So in here, of course, as we look, negative root 7 is not in the interval. So that means that we're not going to include negative root 7. On the other hand, root 7 is definitely a member of that interval. Thinking about it this way, root 7 is between root 4 and root 9, which means that root 7 is between 2 and 3, which means it's definitely inside our interval. So there is the one value guaranteed by the mean value theorem. And in fact, that means our only answer is x equals the square root of 7. So oftentimes you'll see in my work, I'll write x equals square root of 7 only, although the only is not going to necessarily cost you anything. So with that said, just to kind of confirm this, we've gotten our single value. The question that's worth asking is, of course, does this produce a parallel tangent line? Let's go look at Desmos really quick to confirm. Okay, so what I've got in here on Desmos is I've got the function itself, x cubed minus 1. Now we know it's just pretty much a cube root function that's just been shifted down a little bit, so there's nothing really fancy there. In fact, we can see its intercept matches. Those things look really good. I've just distorted the window so we can see this a little bit easier. So in here we've got the point 1, f of 1 and 4, f of 4. And let's actually label those just so we can see them on our picture. And then I've also constructed the secant line through those 2 points. So we can see that those guys are on there. Everything looks pretty good. That looks better, but whatever. Oops. There's our stuff. So from here, what I wanted to do is I wanted to verify that the tangent line at root 7 was actually parallel. So let's take a look. So it looks like right there, 2.646 is our tangent line. Those things look pretty darn, parallel. Now it's worth pointing something else out. Remember we mentioned that we actually got two values. We got negative root 7 as one of our values instead. If I put in negative root 7, you'll see that although it's a little bit harder to tell, we clearly look like we do have parallel tangent lines there as well. But at the same time, the difference is, notice that this x value, negative 2.646 or negative root 7, is outside the interval that we were looking at. We had 1 to 4. We're trying to guarantee the one that's in there, so we ignore that one, and instead we focus on the one that's inside our interval, which was positive root 7. So in a sense, it looks like we've done everything well. We've gotten the values out of it that we have, and we've seen the mean value theorem in action one time. So pretty good start. This would be a great time if you have questions to kind of talk about it if you can. Otherwise, let's move on to a second example, just to kind of help get you comfortable with this technique. Okay, our second example that we're going to hit is a rational expression. So our rational expression here, we are asked to find the value guaranteed by the mean value theorem for the function 5 minus 4 over x, on the interval from negative 1 to 4. So we're trying to find the place where the tangent line is parallel to the secant line through those 2 points. So this is one of those really important problems. And here's the reason why. With this problem, if you barrel into the situation and just start working through, you'll end up in a really awkward spot. In fact, watch this magic. If you just jump right into the average rate of change equaling the derivative, here's what's going to happen to you. Everything will feel just fine as you begin. So if you plug in 4, you're going to get 5 minus 1 is 4. If you plug in negative 1, you get 5 minus a negative 4, which is 9, all over 5. You get negative 1. And if we set that equal to the derivative, f prime of x is going to be equal to positive 4, or so let's see, do this correctly, 0 minus a negative 4 over x squared. So ultimately, the equation we have to solve, would be -1 equals 4 over x squared. Now I realize I moved really quickly through and my color scheme seemed to switch because I skipped a step. The reason I wanted to skip that step was to illustrate how important that very first step here about verifying that the mean value theorem applies actually is. In our situation here, we end up with the equation -1 equals 4 over x squared. And if you move some stuff around, you'll very quickly get the equation x squared has to equal -4. Now you know how to solve that. In fact, you could probably off the top of your heads get x equals -2i, comma positive 2i. But there's a problem. 2i don't think that you're allowed to get imaginary values here because they're not on our interval of real numbers. Like, we should be able to get a real number value out if the function actually applies. So this is sad panda time. This is not good. We don't want that. Just like, no. Like, we don't want that. And in fact, the reason is we slid through that very first step. I'm sorry, I can't fake it. I'm just so used to verifying properties. But take a look at this first step. We're supposed to verify continuity and differentiability. Well, to consider continuity, the first thing that catches my eye about a rational expression is when the denominator equals 0. I see that there's a vertical asymptote at x equals 0. Well, here's the problem. 0 is in between -1 and 4. It's right smack dab in the middle. So what's happened is we've just tried to find a place where the average rate of change equals this value, but we've found it on a discontinuous function. And what seems to be happening here is our average rate of change is negative, meaning that our function probably looks something a little bit like this. So our secant line would look something like that. But then if we try to find a place in the middle where the secant line matches, we never would. Notice this function has positive slope everywhere, and also has positive slope right here on the other side of the vertical asymptote. So we can see that this method actually fails. So the moral of the story here is that there are no such values. And again, we don't actually have to try to solve it, because even if we'd found a value, it wouldn't have been guaranteed by the mean value theorem. There's no such values here because f of x is discontinuous, or let's just say is not continuous. And it's not continuous on our closed interval -1 to 4. So the moral of the story, I like to talk about morals in here as much as I possibly can. The moral of the story in this situation is that you need to make sure that you actually check that the mean value theorem applies. Otherwise, you might spend time on a problem that is either impossible and is going to give you such nonsense as imaginary x values, or you could just spend a bunch of time, get a value, and have it not be guaranteed by the mean value theorem and miss the points anyway. So again, do not forget to check that the mean value theorem applies. That's a really, really essential step of your process. Now, with that said, I want to give you a chance to just try this yourself. I'm going to get to some twisty different situations that'll pop up in just as well, and we will hit those in just a moment. For the moment, I want you to take a few minutes to pause the video in just a moment and try this out for yourself. I want you to try to find the value guaranteed by the mean value theorem for g of x equals the square root of 2x plus 5 on the interval from 2 to 10. I think this is a good medium to medium high level question that involves a little bit of algebra and some thinking. So I'm going to encourage you to go through here. I am going to tell you that in this case, the mean value theorem does apply to this function. It is differentiable on the interval we're looking at and continuous for sure. So if you want to slide through that step, you can. You can tell me I guaranteed it. Why not? That means something. But please take a few minutes to try this problem, and then we'll come back together and I'll overview my work for it. So please pause the video now. Okay, coming back here, just to kind of overview things. The answer to the question, the value that's guaranteed by the mean value theorem, is 5.5, or x equals 11 over 2. And the pathway to get there, after of course taking out the fact that I told you don't need to verify that the mean value theorem applies here, I gave it to you that it did. My average rate of change, g of 10 minus g of 2 over 10 minus 2, was equal to 1/4. And then my derivative actually required the chain rule. So if you got a slightly different answer, like I don't have it off the top of my head what that answer would be, I think that it ends up being like negative something. It wouldn't have been in the interval. So you did require the chain rule here. So you can see my work doing the chain rule all the way down here. Although I'd point out that I think this is one you should be able to do kind of in your head or do really quickly nonetheless. The chain rule though yields our derivative of 1 over square root of 2x plus 5. After that, we need to solve when 1 over 2x plus 5 equals 1 over 4. Looking there, we can flip both sides so that way we get both sides denominators equal to one another. Solving that equation, we eventually get 11 over 2. So again, this one's a little bit more algebraically involved. You had to do a little bit more work, and your answer turned out to be a rational one rather than a nice value of some kind. But I think the process itself should be straightforward and should be easy to follow. So with that said, Where we're going to move from here is we're going to look at some situations that aren't quite as easy to follow, where things just aren't given so cleanly. So without further ado, let's take a look at some of those scenarios. Alrighty, so from here, as I said, what I want to hit next are just a few wrinkles involving the mean value theorems, asking some questions in ways that you might not have been asked before, and hitting a few techniques that you might not immediately seem apparent. So what we're going to hit first is how we might use other tools to allow us to find values guaranteed by the mean value theorem, as well as with some non-traditional functions. So in this case, in the next example we're going to look at, you're asked to find the value or values guaranteed by the mean value theorem for f of x equals x times sine of x for values of x between 1 and 3. So as we did before, it's good to start with that first verification step. And in this case, the verification is a little bit different. So in this case, what I want to point out is that both x and sine of x are both continuous and differentiable. So, and again, I'm going to abbreviate a little bit just for the sake of space. I have a little bit less space here, especially because I'm not sure the green screen is going to work at this point. So both of those two functions, x and sine of x, are continuous and differentiable. It's also true that their product is going to therefore be continuous and differentiable. Now, we didn't prove this property ourselves in the last unit, but if we needed to, we could, using properties of limits and properties of functions. So again, it's a little bit hand-wavy, but at the same time, at least we've got that there. So this is going to work. This is a function that is continuous and differentiable for all the values, because it's a product of continuous and differentiable functions. So good starting point there. Our next move, though, is the typical computation step. We need to find the average rate of change, or the secant line slope, and then, of course, the derivative, or a way to get the tangent line slope. So starting out with the average rate of change, we'll, of course, have our difference quotient like normal, f of 3 minus f of 1, all over 3 minus 1. But when we calculate that, we get some uncomfortable expressions, I'd say. F of 3 will be 3 sine of 3, and f of 1 will be 1 sine of 1. So I guess if you want to put that 1 in there, you can. It just looks like absolute value, so I'm going to do that. And all of it is, of course, over 2. So the average rate of change is a little weird because we get 3 sine of 3, and neither of these is an evaluable, or we can't get a nice value for those things. Like, they have values, they'd be decimal values, lots of ways to get there, but we don't know those values off the top of our head. They're not special right angle or special triangle angles. So from here, we've got that awkward expression, and then next, when we go to compute the derivative, looking at that expression, we already noted that there's a product there. We're going to need to use the product rule. So in this case, our derivative is going to be fairly complicated. So we know how to do this, but again, we'll play it safe since we're doing it in class here. So we'll have the derivative of x times sine of x plus x times the derivative of sine of x. So this simplifies pretty nicely into 1 sine of x plus x cosine of x. So our derivative is involved. From there, we know that our job is then to solve the equation. Like, we're trying to find x values on a particular interval, so we solve the equation that equates the average rate of change and the derivative. So in our case, that's going to look like this. 3 sine of 3 minus sine of 1 all over 2 equals sine of x plus x cosine of x. Now, I don't want to preclude the possibility that you are the greatest algebraic solver in the history of the entire human race. So don't feel insulted when I say this if you are that person. But I don't think anyone here has the ability to do that off the top of their head or to do it without any sort of extra help. In fact, in this case, we don't have any way to isolate x on the right side more than anything else, which tells us that this is not actually a function or a solution we can find by hand. This is a problem that requires the help of a calculator. So at this point, and you would have known this on the assignment if you were doing it yourself, because I would have told you on the assignment that it was a calculator question. But for the moment, like playing along, we've got to solve that equation. So what I'm going to do is I'm going to use the graphing calculator's intersection ability. So first I'm going to input both sides of the equation. So you may have seen this before, but I'm going to use the fraction piece just to make entering that numerator easier. So that's going to be 3 sine of 3 minus what is 1 sine of 1. All of that's going to be over 3 minus 1, also known as 2. And then from there, for the second one, we need to put in that derivative that comes from the product rule. So sine of x plus x times cosine of x. And recall, if you've forgotten or if your calculator fights you on this, make sure that you put that multiplication sign in there. Some calculators fight you on writing x cosine. They think it's all one expression. So in this case, I just put everything easy in there. So now if I just go to graph this on the standard window, you'll see that there's a lot of values in there. And that can make things a little bit intimidating. You might feel like there's an infinite number of answers, and in fact there are. There are an infinite number of places where the tangent line has this slope. But remember, the final piece that we need to go through is to check that our values fall on the open interval that we were interested in the first place. So to help me isolate that, I'm going to change my xmin and xmax, my x window, the horizontal range of my window. I'm going to change that to 1 to 3, because that way we'll be able to isolate all our values. And then second, because in that last picture when you looked at the graph, our slope value, our average rate of change, thank you, our average rate of change was very close to 0, I'm going to also zoom this in a little bit. I'm going to let my ymin be -2 and my ymax be 2. Again, that's just speculation, but I figure that it's just kind of nice to see. That way I can see some separation. And look at that. There's only one value in the middle that we need to find. So just kind of helping us really quickly here. I forgot that I should put these into the notes so it's clear where this stuff came from. So we graphed the stuff. We, looking at our graph, are now going to find the intersection. So enter, enter, enter. And it looks like our intersection is at x equals 2.104. So let's see. X equals 2.104. And so there's our value. Notice that 2.104 is in the middle of our interval. In fact, I'll just do that. Switch colors one more time. It's in our interval, so I feel confident that we found our correct value. So again, on a homework assignment, on an exam, you'll know to use a graphing calculator because it'll be on a graphing calculator section. It will explicitly say that. But at the same time, keep in mind that for those problems that we can't solve algebraically, our graphing calculator is handy. And in fact, even though I didn't show it, there are ways to even be more careful and to show this intersection happening. So just know that's one kind of little wrinkle that might pop into your work as you're working through the mean value theorem. Second, I've got, of course, a table problem. We've looked at some things numerically so far, but I think this is a really good thing to bring up. So in this example, we're told that g is a differentiable function and that there are values of g given in the table below. Our question to answer is there a value between 0 and 6 for which g prime of c equals 2? And our job is to justify our answer. So in this case, there are usually a couple different ways to go through. In our particular problem, we're given values of g, not g prime. And if we'd been given values of g prime, we might have been able to look and use something like the intermediate value theorem to say that, well, g prime falls between here and here. Unfortunately, given values of g, since we want, let's write this, kind of track it up here. Since we're given g, but we want g prime information, that is classic notice that we should be using the mean value theorem, because the mean value theorem connects the average rate of change of g to values of the derivative g prime. So basically this is, although it doesn't seem like it, it's certainly not flashing at neon lights at us, this is actually a mean value theorem justification question. And so with that in our mind, recall that there are two things that we need to verify in order to use the mean value theorem. We need to verify that we have continuity, and it's specifically continuity on the closed interval, which in our case would be the closed interval 0 to 6. And second, we need to guarantee that we have differentiability. And differentiability, though, is only required on the open interval. So in order to proceed forward and to try to use the mean value theorem, we need to first verify that the mean value theorem even applies to our situation. So we somehow need to conclude that this g function that's just shown in a table has both continuity and differentiability on appropriate intervals. Well, looking up at the statement at the beginning, it starts by saying let g of x be a differentiable function. Because g is differentiable, we know that there's a lot of implications that come from that. G prime of x is continuous, and even more importantly, since differentiability implies continuity, this tells us that g is also continuous. So therefore, as we start off our work here and we try to answer this question, a good place to begin is with that verification statement. G is differentiable. And of course, I can't write fast. G is differentiable. So it's trying to phrase this just right. I know what I want to do. I'm going to make a quick little substitution here. I like to say these exactly the right way. So first, since g is differentiable, g is also continuous. That way it's clear that differentiability is the condition that leads us to continuity as well. Next, with the mean value theorem, we've gotten continuity and differentiability. Remember that second step that we hit is in talking about the average rate of change. So what we want to see is what does the average rate of change tell us about G? Does it tell us anything about G prime? So looking in here, let's just compute what the average rate of change is. And for the moment, you can consider this kind of a speculative move. Like we're just thinking that, well, let's try this. Especially in a mean value theorem scenario, let's just see what happens if we take the average rate of change. Excuse me. So based on the table, we'll get 22 minus 10 over 6, which is 12 over 6, which is 2. So what we've just shown is that G is differentiable and continuous, and the average rate of change equals 2. Well, thinking about this, that's all we really needed to show that G prime of C equals 2 somewhere on that interval. So to finish this off, we can therefore invoke the mean value theorem, which just means use it to justify your conclusion. So from here, thus, by the MVT, and it'd be nice to spell out mean value theorem, but I'm a little bit lazy right now, it's getting late. So thus, by the mean value theorem, G prime of C has to equal the average rate of change, and in our case, the average rate of change is 2. So G prime of C equals 2 for some value C in that open interval, which was between 0 and 6. And that is exactly what we were trying to prove. So our question is, in a sense, answered. We used the mean value theorem to get there. Now this question kind of comes out of nowhere, or comes out of left field, because it's just kind of a bald, kind of weird question, given a table and stuff. But the truth is, this has been asked on, I believe, each of the last 3 AP exams that I've gone to Kansas City to grade. So this is something that's valuable to see. And things that are worth pointing out is that you do have to actually state this thing. It's a little uncomfortable because we should know at this point that differentiability implies continuity, but that's how we communicate the reasoning that we're using. Otherwise, it's unclear whether or not you just took it as given, or if you didn't understand it was necessary. So make sure that that's there, make sure your difference quotient is there, and make sure that you invoke the mean value theorem appropriately. And again, this is one of those kind of archetypal explain and prove questions that we use with the mean value theorem. So something to definitely be prepared for and be on the lookout for. Okay, from here, the last thing I wanted to hit is I just wanted to very briefly go over something that I consider a corollary of the mean value theorem, and it's called Rolle's theorem. And for a long time, in fact, including in high school, I remember learning Rolle's theorem first. But the truth is, Rolle's theorem is just a special case of the mean value theorem. So let's see what it actually says. And if you want to write it down, great. You will not be tested on this without me stating Rolle's theorem for you, in case that comes up. So Rolle's theorem says, let f be continuous on the closed interval a to b. Sounds kind of familiar. And differentiable on the open interval a to b. That also sounds familiar. If f of a equals f of b, then there is at least one number c in the open interval ab, such that f prime of c equals 0. So, thinking back this through, this is very much like the mean value theorem, including the fact that we're guaranteeing that there is at least one number c such that f prime of c something. So in here, the difference is, and I hope you can notice the differences. I'll highlight them in a very bright color. I'll use green here. First, it notes that f of a has to equal f of b. So that means that our two endpoints have to be at the exact same height. So over here, for instance, if this is a and this is b, ignore the fact that those are very unstraight lines, my bad. If that's a and that's b, the two heights have to both be equal. So they should be at the exact same y value, which it looks like they are. If that's true, it then says if f of a equals f of b, then there is at least one number c in ab such that f prime of c equals. Now, normally we're used to that saying equals the average rate of change. It equals f of b minus f of a over b minus a. Well, think about this, though. So this little change here. Our normal thing says f prime of c equals f of b minus f of a, all over b minus a. In other words, the average rate of change. We'll add in this extra requirement that f of a has to equal f of b. If that's true, our average rate of change is equivalent to f of b minus f of b over b minus a. But f of b minus f of b is 0, which means our average rate of change is 0 over something that's non-zero, which means the average rate of change is actually equal to 0. So all this is the MVT with the average rate of change equal to 0. And I can't write this fast enough, I'm sorry. So with that said, of course, you can kind of see what's happening here. If we look at those values, we're guaranteeing that there's some value c in the middle where the tangent line is parallel to that secant line. Okay, come on. Really? Decided to fight me here. Let's see if I can try it again. There. So here is our secant line. And it says there should be some value in the middle where there's a tangent line that's parallel. And since that's a horizontal line, because it's going from the same y value, between the same y values, that means that there should be a value c somewhere in the middle. Not necessarily at the midpoint, by the way. It just happened to look that way, where the tangent line is parallel. And of course now, that brings up the question. Like, I don't think this is too crazy. All we're doing is getting a special case where the endpoints align in just the right way. In other words, it's still the mean value theorem, just a special average rate of change. The interesting thing, though, is the fact that by guaranteeing that there's a place where the derivative is equal to 0, what we've done is we've guaranteed that we have a critical number. So in other words, if we're on some interval and we know that there's a place where the derivative equals 0, ding, 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 that means that we're at a critical number. So the Rolle's theorem, or Rolle's theorem in itself, is useful because it gives us a way to narrow down and focus in and say that, hey, there's a potential relative maximum or relative minimum in this interval, simply by looking at the endpoints and then invoking the mean value theorem. So, and in fact, I guaranteed a critical number in that interval. So again, it feels a little bit weird, and in my mind, it doesn't seem important enough simply because of the fact that the mean value theorem's out there, and you could just apply the mean value theorem and get the same thing. But it's that special case of having f prime of c equals 0 and provide a critical number that makes this a theorem that deserves some attention. So it's just a way to find a potential place where we have a relative max or min. Almost like the intermediate value theorem lets us say that there's a 0 between here if we have that sign change behavior. In this case, we're saying if our endpoints are at the same spot and our function's continuous and differentiable, there's a spot in there where we might have a maximum or minimum. So you should investigate. So with that said, what I wanted to do is I wanted to hit one quick example involving Rolle's theorem just to kind of illustrate it once, and then we'll call it a day and wrap this lesson up with a quick little review. And again, I apologize because there's like swirling, weird, digitized looking things around me. It's just getting late in the day and I need to finish the video, so it's just not going to look as good. So in our example, we are asked to find the values of c guaranteed by Rolle's theorem for f of x equals x to the fourth minus 2x squared on the interval from -1/2 to 1/2. So in order to work your way through here, although I don't have the steps for the mean value theorem, they look very much the same as what we had before. Our first step would be to verify, and I'd point out here really fast. That's a terrible looking f. Got an f for writing that f. F of x is a polynomial, so that means that both the mean value theorem and Rolle's theorem are going to both equally apply. So f is continuous and differentiable. So we're good there. That's automatically given by its polynomialness. So we're covered there. So the mean value theorem definitely applies. Now in order to use Rolle's theorem though, specifically Rolle's theorem, there's that extra requirement that we have. And you'll recall what that requirement is. We need the endpoints to be at the same spot. So in addition to stating whether or not f is continuous and differentiable in an appropriate way, we next need to look at what is f of 1/2, and second, what is f of -1/2. Like without that, we won't be able to make any guarantees about Rolle's theorem. So if we plug in 1/2, we get 1/2 to the fourth minus 2 times 1/2 squared. Of course, this couldn't be instantly easy. We're going to get 1/16 minus, it looks like, 2/4. And finding a common denominator really fast gets us 1/16 minus 8/16, which is -7/16. So good enough stuff. If we do -1/2 to the fourth, we're going to get the same value as 1/2 to the fourth. It's an even power. And then if we get minus 2 times -1/2 squared, we're going to get the exact same value. So I'm going to go ahead and point out that for this one, we also get -7/16. So works out really nicely. Like we're in pretty good shape here. We've got the two same values. So again, that tells us that f of -1/2 equals f of 1/2. So in other words, Rolle's theorem applies. So a quick little check here isn't just as simple as it was before, where we just had check continuity and differentiability. We also need to check the endpoints. Now that we have them, though, like the rest of the problem becomes very simple. Are solving the average rate of change equal to... Sorry, I got to do this correctly. We don't have to write this step, but just to illustrate what's actually happening here, I said this is just a special case of the mean value theorem. So in other words, what we're really doing is we're trying to solve this equation equal to f prime of x. Well, we already know that f of 1/2 and f of negative 1/2 are both the same. So that means the numerator is 0, which means our entire fraction is 0. And finding f prime for this function is really easy. It's 4x cubed minus 4x. So all that's left is for us to solve this equation. So let's do that. We can factor this out. I'm going to factor out, in fact, a GCF of 4x. That'll leave me with x squared minus 1. And from there, if we set that equal to 0 or factor it further, no matter what we get, we're going to get that x is equal to negative 1, 0, and 1. So there are 3 such places where we're going to have a slope of 0, and therefore a candidate to become a relative maximum or minimum. So Rolle's theorem should theoretically guarantee a value. But remember, the last piece here is always the same. We need to actually figure out which ones fall into the correct interval. So we're supposed to be in the interval from negative 1/2 to 1/2. Looking down here, only 0 is in the open interval negative 1/2 to 1/2, right? Because negative 1 and 1 are both outside that. So that tells us that the only answer that's guaranteed by Rolle's theorem is x equals 0. So that tells us that we've got one critical number at x equals 0. And in other words, it's a good place to investigate. On this interval, we should have a critical number, and we might have some sort of relative extremum. So finally, just to match things up, as I remind you, like this is just an extra thing. It's just a special case. I figured it was worth exposing you to. I'm not putting any on your problem set for the night or anything, but it's nice to have it out there, and it's good to have been exposed to it. But otherwise, let's do a quick little overview of what we hit in this lecture, and then call it a day. Give you some extra time here. So if you recall at the very beginning, we talked about the original 2 value theorems we had. The intermediate value theorem, which guarantees that there's an x value to go with all the between y values of a continuous function. And the extreme value function, which guarantees there's a high and a low point for a continuous function on a closed interval. To that, we added the mean value theorem, which guarantees that there's a place where the average rate of change and the instantaneous rate of change are equal. What that amounts to equation-wise or algebraically is solving the equation of the derivative equal to the average rate of change. Graphically speaking, though, that's finding where the tangent line is parallel to the secant line that goes through the 2 endpoints. So we talked a little bit about that graphical interpretation and looked at some instances of where it worked, and we investigated why it is that our theorem requires f to be continuous and f to be differentiable on an open and closed and open intervals, respectively. Beyond that, we actually started working through the problems. We realized that our approach started with verifying to make sure that we weren't getting tricked and we weren't finding a situation that didn't allow for the mean value theorem. Then we just computed the 2 pieces, the average and instantaneous rates of change. We solved the equation, and then we checked to make sure our answer was in that interval. I can't stress that last step enough. As someone who's written many a question, it's very easy to trick somebody or to have someone lose some points by forgetting to verify that they're in the correct interval. We're only talking about values inside that interval. Those are the only ones that are guaranteed. There might be others, but they're not relevant to our discussion here. Beyond that, we looked at some situations that didn't work, and obviously we pointed out how important it is to check and verify first, because if you don't, you might end up getting imaginary answers, and then you're just going to earn imaginary points in the test, which might sound good in Algebra 2 or Math 3, but not here. Beyond that, we did a fairly challenging try that brought in some extra pieces, required the chain rule, looked at some issues that were there, but it works out really nicely otherwise. After that, we looked at how we could use the graphing calculator to get there, changing nothing, just really using the graphing calculator's solving ability more than anything else. And we talked about how we could guarantee there's a particular value with a constructed question that resembles some of the things that you've seen on the recent AP free response sections. So we looked at all those pieces, stated it nicely, and then finally we talked briefly about Rolle's theorem and did an example to let you see where that was, reminding us that the only real value here is that you could potentially find a relative maximum or minimum. With that said, I know I don't feel like this lesson was as clean and crisp as the previous one was. No real reason for that. Just had trouble kind of lingering through here and ran out of hours in the day, which is why the green screen kind of went out. Hopefully still this has been informative. Remind you that if you have any trouble on the homework assignment, those tougher questions and representative section or problems from each section are in the video solutions for the assignments. And without further ado, again, wish I was there with you, but in my absence, hopefully this time-traveling video teaching you about the mean value theorem has been sufficient. Have a great day, and virtually see you tomorrow.